Good evening, students. Am I audible and visible to all of you?
Yes, ma'am.
Okay, should we start the class? Okay. So in the last class, this is the last thing which we discussed, that how the molecules are formed or how the bonds are formed between the atoms, which gives rise to the molecules of molecules of a compound. Is it correct or not? That I think that was the last point we discussed in the last class, right? So moving on, we will build up on the certain more concepts. The two main concepts which we have to cover are molecular orbital theory and hydrogen bonding. Can Ritika please tell me that whether have you heard about MOT or molecular orbital theory?
No, ma'am.
Okay. Which chapter is going on in your school? Please apprise me.
Ma'am, they have just started this chapter, ma'am.
Okay. So you are ahead of your class. That should be good. Whatever I had taught you should be clear to you. You should be able to better understand or revise the concepts, whatever we have done in the class, right? So moving on, this is one of the charts which I got it in NCERT. And interestingly, this is hybridization involving the d orbitals, right? Now look at these hybridization type carefully. What did you notice? Shweta, do you notice something which we might have missed or we need certain explanation? Hybridization.
The shape of the orbitals?
Yeah, do you?
Can
Yeah, sorry. Please speak, Shweta. I'm just waiting.
are you asking like what other shape is missing?
No, I was asking that hybridization type. You can see DSP2, sp3d, sp3d2, sp3d2, d2sp3. Is there any name which is unique, which we might not have discussed in the class?
D2sp3.
Okay. See, basically, it is the hybridization involving the various orbitals of d having d electron in them, right? Now, the major point of concern is, till now, whatever we have learned, the types of hybridization, I'll put it here again. We have talked about sp, we have talked about sp2, we have talked about sp3, right? And we have talked about sp3d, sp3d2, sp3d3 maybe. Now, the point of discussion is that dsp2 and sp3d2. Why at some places we have kept that d at first place, right? Like in the case of nickel tetracyanide, you can see the type of hybridization is dsp2. Then pf3 or pcl3, sorry, pf5 or pcl5, it simply becomes trigonal bipyramidal shape, and hybridization is sp3d2, right? So at two places you can see dsp2 or d2sp3. I believe that my point is clear to all of you, that what do I want to say, why we have written sp3d2 and why at some places we have written d first. That is what we need to understand, right? So I'll pick up one of the examples from the first category. I will take up nickel tetracyanide and explain it to you when we have to write dsp2 or when we have to use sp2t, right? Can somebody tell me the atomic number of nickel or valence shell configuration of nickel? When we were doing periodic table, I told you to remember the periodic table horizontally in case of P block element and S block element. For D block elements, I'll suggest you learn the entire row. It is scandium, titanium, vanadium, then chromium, manganese, iron, cobalt, nickel, copper, and zinc. If you ask me the atomic number, just after calcium, scandium is there. So this is 21, 22, 23, 24, 25. It will move till 30, right? Now talking about the valence shell configuration of these elements, if scandium is having 1 at the end, it will have D1. That's just my observation. There is no fixed rule for the other. See, the elements falling after scandium or titanium. It's just an observation that we call this series as this is called as first transition series. These are the 10 members of the first transition series. Whatever is the second digit, right? You remember that zinc was having D10 configuration, right? There will be an exception at copper and chromium. They will be having, it will be having S1, D5, and this one will be having S2, D10. Sorry, rather S1, D10. Is it clear? If somebody asks me for nickel, I must remember it will be D8. Since it is the first transition series, or this is the third period, so it will be having 3D8, 4s2 in its outermost or the valence shell or the electrons which participate in bond formation. Till now, we have learned only that the valence shell electron take part in the bonding, or they do take part in the bonding. But the moment we talk about the D block elements, the D electrons also take part in the chemical bonding. So if I have to find the structure of nickel tetracyanide, I will be writing the nickel in ground state. Even if I don't want to write, I can skip that script. But my purpose of repeating it, that dear students, please pay attention, become masters of your chapter of periodic classification and structure of atom. You will come to know, or you will understand, rest of the chapters become very, very, very easy. So I have two choices. I will have to just write, because my work can be done only by the 3D84S2. So I can simply proceed to write to configuration of or draw nickel in ground state. I will draw it like this. 1, 2, 3, 4, 5. Right? I'll be drawing 3D, then I will draw 4S, then I will draw 4P also. If required, we can draw even 4D, because you understand that the 4S and 4P will be the part of the valence shell, right? So 3D8 means we will have 5 unpaired electrons, and then we will have 3 paired. We are having a total of 2 unpaired electrons, right? Now, just look at the hybridization which is given to you. You just need to cram it or just remember it. They're saying DsP2, right? What you have to do? You have to have 4 orbitals of equal energy. So what will happen? That 2 electrons from 3D will be promoted to 4s and 4p, right? So we will have nickel in excited state and as a result of it, we will be having 1, 2, 3, 4, 5, 6 electrons will be left here. And then 4p will be filled. Do you agree to this configuration? Ananya, is this chapter done in your school or not? Ritika, is it over in your school?
No, ma'am.
Okay. I have a request for all of the students. Either you please switch on the cameras, or sometimes I'm not able to understand whether you are grasping it or not. Since it is slightly more important and more difficult topic, please, and it is, I will tell you, it is exceptionally theoretical in nature. Right. So I will try to make it as interesting as possible for you. And as I'm getting to understand that you are not able to grasp most of it probably, or some of it, let me limit my lecture to this point in this particular topic. DSP2 means that D is of lower energy. Even if I remove this step, if you want, you will have to tell me. If you want, I will teach you in detail. If you want to teach me in short, I will teach you in the short. Let me put my point across, and after that you can make your decisions. See, when we say DSP2 and SP2D, the difference is that in DSP2, the D is of lower energy level. As you can see, it is 3D. This is 4S and this is 4P, right? But if I write SP2D, all of them will be belonging to the same principal energy level. That is, this will be 4S, this will be 4P, and this will be 4D. That is the meaning, or that is the reason we have to be very sure that which D is participating. At the beginning, when I tried to tell you that 4D can also be drawn here, that is a bit higher concept. More details will be taught to you in class 12th, right? So once your school teacher finishes your chapter, please let me know that what they have taught you. They might have a chance to skip it, but still she can give you or he can give you a 1 mark question from them. So from my side, I will say that this particular chart is in NCERT, so we must know it is important to write. Even if we are cramming, we are not understanding, we are cramming, we need to write DSP2 wherever it is written as DSP2, because in this case, the hybridization is involving N-1 level D. If it is written SP3, you must be remembering PCl5. We must have discussed it in the class. Have we discussed the hybridization of PCl5, Shweta, in the class? I assume we have discussed, otherwise you would have said it, right? So on that note, let's move on it. I'm again repeating for the last time that DSP2 means that, or anywhere wherever D is written first, that means that we use a word, we say in such hybridization, inner D is used, right? And whenever we are writing SP3, D, that means SP3 and SP and D, all three belong to the same principal energy level. Even if we want to go ahead like this, we can and we should. But moving on into class 12, there is a chapter D and F block elements. So please don't think that hybridization, whatever we have done in class 11th, is going to be useless. It will be the building block. Else what we have to do, we have to have a capsule course, or we have to do the revision of a particular topic before we land up in that particular chapter of class 12. So moving on, we will be talking about the molecular orbital theory, or it is called as, commonly, as I told you, it is called as MOT. We have understood that atoms combine to form molecule, right? If these are two atoms of hydrogen, they are combining, that is, area of overlap is becoming common, then hydrogen molecule is formed. So the scientists believe that when atoms combine and form molecule, the atomic orbital in which the electrons are being filled or electrons were kept or held, they change into molecular orbital. And based on those molecular orbitals, we have a molecular orbital theory. Now, this molecular orbital theory was given by Hund and Mulliken. They have given us many concepts. One of them is molecular orbital theory. So we will be, first of all, understanding what are the important points of molecular orbital theory, right? So the first point is that atomic orbitals of comparable energies and proper symmetry combine to form molecular orbital. What do we mean by this particular statement? Comparable energy means that 2s and 2p have a comparable energy. They can combine. Proper symmetry means that px can combine with px, right? Px of one atom and px of another atom may move together, come closer and overlap. But it will not happen that 2px of one orbit of one atom and 3px of another will combine. Never. Is this point clear to all of you?
Yes, ma'am.
Okay.
Ma'am.
Okay. Then an electron in an atomic orbital is influenced by one nucleus, while in molecular orbital, it is influenced by more than one atom or more than one nuclei. See, if I say this is an atom, this is the nucleus, and this is the electrons, many electrons are there, assumingly there are many electrons into it, right? So what happens here is, we say that these two electrons, they are present in these. What is this? This is an atomic orbital. This electron is under the influence of one nucleus only. As long as they are not forming bond, it is just attracted towards only this atom, or the nucleus of this atom. But when it changes into molecular orbital, right, that means another atom similar or a different may be approaching it, and the atomic orbital will convert into, let's say this is a molecular orbital. We write it in short form MO, molecular orbital. There will be two nucleuses now. All the electrons will be under the influence of more than one nucleus. That is the meaning of this point, that an electron in an atomic orbital is influenced or affected by one nucleus, while in molecular orbital, electron is influenced by two or more nuclei, right? Then this is technically, we use a term that atomic orbital is monocentric. Mono means always, mono is alone or one, right? You may be, we use this the prefix mono many a times, right? And interestingly, I wish to tell you that my nickname is Mona. So, and later on I realized, when I had a discussion with my father, I realized that he wanted to have one daughter and many sons. So he named me Mona, because mono means alone or the unique one, right? So sharing this thought with you is simply trying to develop a correlation. How do you understand, or how do you at times make memories in your mind or correlations in your minds, right? Because we cannot understand, we cannot learn, if we can understand everything, we can learn everything, but reproducing something, that means writing an answer, becomes an art. So at times I would prefer to teach my students how to develop a correlation between two things and remember them, right? So that was just a small story to break the monotony of the class also. So the atomic orbital are monocentric, that is, they are governed only by one nucleus, or they are affected only by one nucleus, while the molecular orbitals are polycentric. Poly means many, as you know. They are usually governed by two nucleuses, right? The next point, the number of molecular orbitals is equal to the number of combining atomic orbitals. If 1s and 1s, 1s of one atom and 1s of another atom are going to combine, they will produce two new molecular orbitals, right? If 4 atomic orbitals are combining, they will form 4 new molecular orbitals. Are all the points listed on the screen are clear to all of you?
Yes. Ma'am.
Okay, good. I believe you must have noted down, or do I need to wait for you?
One minute, ma'am.
Okay, please tell me when, let me know when you are done.
Done, ma'am.
Okay, good. So, as I told you, the atomic orbitals combine to give you molecular orbitals, right? Now, these molecular orbitals, as you can see on my screen, are of two types. One is called as bonding molecular orbital, and the other one is called as anti-bonding molecular orbital. Now, anti means anti means opposite, or something that if you are going in this direction, the other person wants to go in that direction, right? So, the bonding molecular orbitals are formed by the constructive overlap. As you can see, they are having more area of overlap in the first case, right? This hydrogen is having one electron in the 1s shell, and this hydrogen is also having one electron in 1s shell. They are overlapping, they are forming a bond, or rather molecular orbital like this, right? And this is called as sigma bond. The anti-bonding or the destructive overlap leads to the formation of anti-bonding molecular orbital, right? You will not be asked to draw them. It's just taken from a older NCERT book, how they used to depict it, right? So molecular orbitals are of two types: bonding molecular orbital and anti-bonding molecular orbital. Now, can somebody tell me how many types of atomic orbitals we have learned? Do you remember the shapes of atomic orbitals? One day, I believe I told the entire class that I took the experiment or an activity with the onion rings, and I showed you something. When I said the orbit is elliptical in shape, Something which is very near to nucleus, the things become far apart from that. Can anybody tell me? Okay, let's make it much more simpler. What is the definition of Aufbau principle? What happened? You don't remember Aufbau? Have you revised the atomic structure till now or not? Are you having your exams in your schools? Ananya, please respond. I'm not going to scold you, but I need to understand it.
Mom, I forgot. I'll revise it once.
Okay, good. What about you, Shweta?
Yeah, I'll revise it once.
Okay. Ritika?
Mom,
Yeah.
what was the question, ma'am? I wasn't able to hear.
I just want to know the concept of Aufbau is clear to you or not?
Yes, ma'am.
Okay, then how do we define Aufbau? See, I'll tell you one thing, students, that in the state of the changing world, like we are going from the classical rote memory based examinations to the practical based examinations. What the NEP people have thought, they will give you the entire definition and they will ask you to find which of them is a correct definition of anything about horns, polys, whatever they want to, right? So it is important for us to at least know them. Once the chapter is done, please go through the entire basic definition and you will see throughout the year, this year as well as the next year, the basics keep on repeating after a certain time or in certain chapters. So my question was, what is an atomic orbital and what is Aufbau principle? Just to refresh your memories, I'll tell you. Aufbau principle told us that electrons are filled in the increasing order of energy in the atomic orbitals, right? And then we understood this Euler diagram. 1s, 2s, 2p, 3s, 3p, 3d, and then 4s, 4p, 4d. The reason for putting it up here is just, I'm not writing the entire one, just making you remind. I understand all of you are bright and the laborious students. You will understand, recall it, and you can, at the end of the class, you please refer to your notebooks, refer to your books, and come back to me if you still have a doubt in it. So atomic orbitals are of 4 types: S, P, D, and F. They can have maximum of 2, 6, 10, and 14 electrons. That was the answer to my question which I was asking, right? Before I tell you how many electrons a bonding molecular orbital or an anti-bonding molecular orbital can accumulate, it must be clear to you or reminded to you that atomic orbitals are of 4 types and they can have 2, 6, 10, and 14 electrons. I understand, you know that, but it's a matter of time. It will be, you will revise them and will be easier for you to answer the question, right? Because at times we ask for the comparison between atomic orbital theory and molecular orbital theory. We may be, the question can be differentiate between atomic or AO and MO with reference to the types of orbital, with reference to number of electrons. May not be, a classical case that you are asked to write these 4 points, right? It may be that any one of them can be given and you are asked to compare it with atomic orbital theory. So let's move on with the fact that molecular orbitals are of 2 types, bonding molecular orbitals and anti-bonding molecular orbitals. Bonding molecular orbitals are, or rather I'll say anti-bonding molecular orbitals are represented by, we say this is a star or asterisk type of a symbol, right? Bonding orbitals do not have such a specific thing there, right? Now, talking about the stability between sp, d, and f, we talked only about their distance from the nucleus, and we talked about how many electrons they can accommodate. Similarly, for the molecular orbitals, we will say that bonding molecular orbitals are of lower energy, and therefore they are more stable. On the flip side of it, the anti-bonding molecular orbitals are having higher energy, and therefore they are less stable. Remember, when we get up in the morning, we are having high energies. That is, we are having less stability. We are jumping over places to have a breakfast, to do this, to do this, to that, right? Then, now, like we said, the atomic orbitals follow the Aufbau principle, Pauli's law of Pauli's exclusion principle, and Hund's rule. They also follow all the 3 rules, right? But I think we have not discussed Pauli's exclusion principle in the class. Have we done that, Ananya, in the class?
Mom, I think we have done it.
Okay. Just after finishing this, we will come back to Pauli's because that's important. And I have identified a common mistake of the other students, right? So should I move ahead? Is this point clear? Okay. Then we say the combination of atomic orbital is done in a certain way, and that is called as LCAO. That is linear combination of atomic orbitals. Sometimes they call MOT as LCAO also. Molecular orbital theory, maybe in a slang, can be referred as LCAO. That is linear combination of atomic orbitals, right? In your syllabus, you will be talking about the homonuclear diatomic molecules. Homo means similar, like H2, B2. I think above then 16, you will know that the electrons are not in your syllabus, right? Like for atomic orbital theory, there is no limit. Out of 118 elements, known elements, anything and everything can be asked. But for molecular orbital theory, we usually talk about only till 16 electrons, right? So this is how it is done. What I have written here is that I have 2 atoms of hydrogen, right? I have labeled one atom as A and the other atom is labeled as B, right? As we know, both of them are going to have 1 electron each, and that electron is moving in orbit, right? Or orbital rather. And when a particle is moving, it will be producing a wave. Now that wave is represented by psi. I believe you understand this word is written, this is known as psi, right? So psi molecular orbital can be either both the waves are moving in the same direction, that is clockwise direction, or maybe in the anti-clockwise direction, that is called as constructive interference or constructive addition. When 2 things are moving in the same direction, they will meet soon. But when they are moving in the opposite direction. Say for example, this electron or electron of this one is moving in a clockwise and this one is moving in the anti-clockwise direction. What will happen? We'll have this situation, right? Psi molecular orbital will be equal to psi A minus psi B. And the first one, when they are both of them are either in the clockwise or anti-clockwise direction, that will be forming constructive one. So that will give rise to molecular bonding molecular orbital, and that will be giving rise to this is anti-bonding, and this is bonding molecular orbital. Is it clear, Ritika?
Yes, ma'am.
Okay. So now, as I have already told you, the orbitals are represented by psi or sigma or sigma star and pi or pi star. Now, sigma star will always be an anti-bonding molecular orbital. Similarly, pi star will always be a anti-bonding molecular orbital, right? There is no need for you to copy down the images. You just have to understand that the molecular orbitals are of two types, bonding and anti-bonding. Bonding will have a lower energy and anti-bonding will have a higher energy. Remember, when we are talking about the hybridization of atomic orbital, in case of methane, for example, we were saying that methane undergoes sp3 hybridization, right? And all the atomic orbitals formed thus are having equal energy. But that does not happen in MO. In molecular orbital theory, we get two types of orbitals. One is having a more energy and the other one is having lesser energy, right? So we need to just understand that thing. Constructive and destructive interference. Constructive will always have a plus sign and the destructive will have a minus sign, right? Now, these are some conditions when the atomic orbitals can combine to give you the molecule. One or two I might have given you in the earlier points also to explain them. As for example, that 1s orbital can combine with another 1s orbital. That means 1s orbital of one atom can combine with 1s orbital of another atom, right? Like both of my hands have five fingers each. They can combine and make such a big, I will say such a big thing out of it, right? But if one of my hand is having, let's say, only 4 fingers, then they will not be able to overlap with each other, right? 5 can overlap, but if I have a missing finger, then they cannot overlap. That's what the meaning here. It is saying that 1s orbital can combine with another 1s orbital, but not 2s orbital, because energy of 2s orbital is appreciably high. Recall the above, where we say that the energies are increasing from 1s to 2s. The energy is more, right? Then we say the combining atomic orbitals must have the same symmetry about the molecular axis. We need to understand with the examples. That is 2pz. Remember, if you have assumed this axis to be z, 2pz of one atom can combine with 2pz of another, but it cannot combine with 2px, which was like this, or 2py, which was like this for the another atom. They cannot overlap. Is this point clear, Ritika, Shweta, and Ananya?
Yes, ma'am.
Okay. The combining atomic orbitals must overlap to the maximum extent. Now, if they are just coming like this, not overlapping, then molecular orbital will not be formed, right? Then we say the greater the extent of overlap, greater will be the electron density between the nuclei of a molecular orbital. That we have seen in case of sigma and pi bonds, right? Do you want to note down something from here or should I move ahead? Shweta, should I wait or should I move?
You can move.
Okay. Now you just note down this, whatever is written here. Just note it down. I'll explain it to you in a moment. Have you noted down the team, the students?
Yes.
Okay. Now, in case of atomic orbitals, we have only one type of the increasing energy diagram. But in case of molecular orbitals, we have two different types of diagrams, or the orders in which the electrons are filled in molecular orbitals, right? Now, before we discuss something about it, let us first of all understand, or can somebody tell me why I have not put up 1sz or sigma 1s2, sigma 1s, sigma 1s, then sigma, then we have two pi bonds. Why? See, now go back to atomic orbital theory again. One s of one atom, one s of another atom B, right? Then we have 2s and 2s of another. Then we have 2p. One is when the 1s orbital will overlap, they will form the sigma bond, because that will be the first bond. When 2s and 2s will overlap, they will form a sigma bond again. But in case when 2p orbital of one atom, 2p orbital of another atom, they overlap, they will form one sigma followed by two pi bonds. The energy of pi bonds will be equal. Is it clear that when 1s orbital will overlap, it will form only sigma. When 2s orbitals will overlap, they will form sigma only. But when 2p will overlap, it will form a sigma followed by 2 pi. Is it clear to you, Ananya?
Yes.
Okay. See, if you understand that, only then I'll be able to make certain explanations for them. If you look at the configuration of elements like boron, carbon, and nitrogen, that means what I am talking? N2 has maximum, that is 14 electrons, right? Among the given elements. And then F2 and O2, they are having 16 and 18. So this configuration, we mean to say, when the total number of electrons in the molecule are maximum 14, you will be writing this. If something is having more than 14 electrons, you will follow this configuration. Ritika, have you noticed any difference in these two configuration? If yes, then what is that? Okay, let's see them one by one. I'll be putting them, every atomic orbital can have maximum of 2 electrons. So if somebody asks me to write the configuration of, let's say C2, how will I be writing that? The atomic number of carbon is 6. Therefore, C2 will become 6 plus 6, that is 12, right? And I will be writing it as sigma 1s2, that is sigma 1s2 bonding. Then I'll put a comma, or sometimes you may miss the comma also. Sigma 1s2 NT bonding, right? Then what we will do? We will write sigma 2s2 followed by sigma 2s2 NT bonding. Then when we come to this one, we have filled sigma 1s, sigma 1s NT bonding, sigma 2s NT bonding. But when we come to pi 2px and pi 2py, please remember, they will be following, as I have told you, they will be following the Aufbau, Hund's and Pauli's exclusion principle. Hund's rule says that pairing of electron will start only when each one of them will receive 1 electron each. Now, once you reach at this point, you know, you have 2 plus 2, 4 plus 2, 6 plus 8. You have consumed your 8 electrons, right? You still have 14 minus 8, that is 6 electrons are still left there. That means you can safely put 2 at 2 pi 2px2 comma pi 2py2. Had there been only 3 electrons here, I would have put pi 2px2 and pi 2py1. Is it clear to all of you? Shweta, can you just respond to it?
Yes, ma'am, it's clear.
Okay. So in this case, we are still left with 6 electrons rather. So what I will be writing? I'll be writing pi 2px2. Then I will be writing pi 2py2. Now by this time, what we have done? We are left with only 2 more electrons, right? So then I will be putting it as sigma 2pz2. I believe we have done a correct work. We have 2 to 4, 6, 8, 10, 12, 14. Is it clear now? So now can you attempt to write it for nitrogen? Please write the configuration for N2. What's the answer, Ananya? Shweta, have you written it?
1 second.
Okay.
Can change it.
Ritika, have you written it? Shweta, can you just state your problem there? Where you are stuck?
What now?
Are you stuck at certain point that you are not able to write the configuration of molecular orbital configuration of nitrogen?
No, ma'am.
Okay, then what's the answer? Ritika, can you explain your doubt if you are having any?
Ma'am, no, ma'am, I wasn't able to unmute myself at that time.
I didn't understand what you said. Can you please repeat, Ritika?
I said I wasn't able to unmute.
Okay. So what is the answer? Can anybody tell me? Okay, I'm not too sure. I tried to say basic thing is we must be very clear in atomic orbital theory. As I have put it in the again that 1s and 1s will overlap to give you sigma 1s2 bonding, sigma 1s2 anti-bonding. 2s and 2s will overlap to give you sigma 2s2 anti-bonding. Sorry, sigma 2s2 bonding and sigma 2s2 anti-bonding. When it comes to the p orbital, pi 2 px and pi 2 py will have the equal energy for, and they will form then sigma 2p z2, then pi 2p x antibonding to pi 2p y antibonding to, and then sigma 2p2. All right. I'm really either there is a I'm not able to understand or hear. Let us take them one by one. We'll first of all, please try to understand the difference between the two configurations. See, sigma 1s2, sigma 1s2 antibonding, sigma 2s2 and sigma 2s2 antibonding are same in both the cases, right? But if you look at the content which I have put in the brown colored box, you will see the moment we come to pi, the p orbital, in case of a smaller molecule from like B2, C2, N2, etc., we have pi bond first, then sigma, then anti-bonding pi, and the anti-bonding sigma. But when the molecules are larger, comparatively like F2 and O2, you can see we have sigma first, then pi anti-bonding, and sigma anti-bonding. Is the difference in the configuration clear to all of you? Students, please respond.
Yes, ma'am.
Okay, the next question which is asked in, see, out of whatever you have learned in chemical bonding, MOT is at the end, I'll say boss of everything. You may not get a question on hybridization. You may not get on a question on Aufbau rule or anything directly. But since this is having the application of atomic orbital theory, molecular orbital theory, by experience, I can say most of the schools ask for a 5-mark question from this particular section, right? So I'll sincerely request all of you to at least speak up your minds, whatever is going on, right? In shortcut, I can say first the 1s orbital will overlap, then 2s, and then 2p. When it comes to 2p, in case of a smaller molecule, the order I remember the way it is that pi, sigma, pi, sigma. Pi bonding, sigma bonding, then pi anti-bonding and sigma anti-bonding. If I talk about the larger molecules, like HF and O2, I will be remembering this order as sigma pi, pi anti-bonding, and then sigma anti-bonding. Is it clear? Remember it for one, pi sigma anti-bonding, pi anti-bonding and sigma anti-bonding for B2, C2, and N2. And then F2 and O2, you will have to reverse the order. Sigma pi, pi sigma. Now the question which is asked in the examination is why the orders are different. Now to answer that question, we have to go back to the formation of sigma and pi bonds. I told you that sigma bonds are formed by head-on overlapping, and they are the first bond which are formed. And pi bonds are always formed perpendicular to the plane of molecule, right? Now we have to imagine that two atomic orbitals are coming closer to each other. So if the molecule is small, the overlap of pi will become easier, right? If this one is the shape of the p orbital, they are looking very large, right? As compared to the, I'll say the, what do we call it? The top of your bottle. I'm not getting the English word for that. Cap. The cap of a Bisleri or any other branded bottle, right? In that case, the molecule is very small. So what happens? If this is the plane of sigma bond, the pi bond has to overlap. Sigma is formed like this. I believe you can see. And the pi bond is formed sideways, right? In case of the smaller molecules, as you can see, assuming it to be a smaller molecule, they will be closer to, one is like this, the another one is like this. They will be pretty closer to each other. But if this molecule is large, that the pi orbitals will be at maximum distance. I think I will just draw that, probably that will give you more clarity, that if molecule is of this size, right, the two atomic orbitals has combined and they have formed a molecular orbital like that. And the pi bonds are at this end and this end. In another case, the molecular orbitals are pretty big, right? And the orbital which has to form a pi bond is at a greater distance. That is the only difference, that for such a molecule, we have to write the, if you ask me, I will dictate you the answer. The answer is that when the molecule is smaller, please pay attention to the first image. If the molecule is smaller like this, that the sideways overlap of the orbitals is easier, and they will easily form the pi bond. That is, pi bond will be formed easily. It will be less energetic, more stable. So in the stability order, the pi orbital will be filled first. But if the size of the molecule is larger, then if the size of the molecule is this big, right, the sideways overlapping will be a bit difficult. So therefore, the formation of the sigma bond will become easier and the pi will be difficult to form. Therefore, the order is different. Ananya, do I need to dictate you to write it down, or you will manage it at your own?
No, I'll write it down myself.
Okay. Now we will take up each one of them, or before that we will understand few more rules and the other concepts which are based on it. The first is that bond order. What is a bond order? Number of bonding electrons, first of all, is we will talk about stability. That stability means number of bonding orbitals and number of anti-bonding orbitals. If number of anti-bonding orbitals is more, then the molecule will be unstable. If number of bonding orbitals is more, or bonding orbital has more electrons, then it will be stable, right? So more the number of bonding orbitals and lesser the number of anti-bonding orbitals having electrons, that will decide the stability of the molecule. Now, what is a bond order? Bond order is half the number of bonding orbitals, electrons, and half subtract number of anti-bonding orbitals, right? If anything is having a bond order negative, that means the molecule is unstable, right? If the bond order has a positive value, only then we can say the molecule is stable. Is it clear to you, Ritika?
Yes, ma'am.
Okay. Now, bond order 1, 2, or 3 will signify the number of whether it has a single bond, double bond, or a triple bond. We'll just see it in a while now. Now, bond length and bond order are opposite of each other. If bond length is if something is having a bond order 3, 2, and 1, you can understand what will be the bond length. Bond length of substance or a molecule having bond order will be greater, right? Then magnetic nature, I believe I clarified this concept somewhere, that if anything is having a resultant or unpaired electron, then that will be paramagnetic. And if it is having all the paired electrons, then that will be diamagnetic, right? So we have already learned about it. It's now what we will do, we'll take the example of N2, right? Which I was asking. Now please respond to it. Number of molecules formed by 2 atoms is 14. Can somebody tell me the electronic configuration of N2 molecule? I'm giving you again 2 minutes by my watch. Please write the electronic configuration of N2. I can come back to the earlier page also for your help. This one. So 2 minutes should be more than enough for you to write the configuration of nitrogen. I'm really unable to understand. Is there any issue or what has happened? Let's begin with the smallest molecule, that is of H2, right? The number of electrons in H2 molecule will be 2. Its electronic configuration will be sigma 1s2. That's what I have taught you. Bond order is number of bonding electrons minus number of non-bonding electrons. It has got only 2 bonding electrons. So that will be 2 minus 0. That is 2 by 2. That will make it as bond order 1. Bond order 1 means it will be having a single bond. The rest of the data about bonding energy and bond length is theoretical in nature. You can always omit it. But for hydrogen, we can say it will have a single covalent bond, right? Now I'm trying to move from the simpler to the difficult molecule. Earlier, I was trying to go for a the two molecules which you must cram or remember at the end of the class, so that you are able to to crack the question, because most of the time we get a question on nitrogen and oxygen only, right? Now, talking about the helium molecule, let's do it quickly. It has got 4 electrons. The electronic configuration will be sigma 1s2 bonding and sigma 1s2 anti-bonding. So what will be the bond order? Bond order will be 2 minus 2 by 0. That means its bond order is 0. Bond order 0 means molecule does not exist. Is it clear to you, Ananya?
Yes, ma'am.
Okay. So that's what we say, that molecule is unstable and it does not exist. Now, if I talk about the boron molecule B2, boron's atomic number is 5, and then it has 10, total of 10 electrons. This is another way of representing the configuration of boron. If you can write with me, I'll be very happy for you. We have to write only till 10. That means what we have to do? We have to put this is 2, 2, 2, 6, 8, 1, and 1. Is it making sense? Atomic number of boron is 5, and 5 plus 5 will make it as 10. So we have to write for 10 electrons. As I explained to you, when you are writing it for something, when you are stuck up at this point where you have a equal energy molecular orbital, you have to put them one by one. So this configuration will become sigma 1s2, sigma 1s2 anti-bonding, sigma 2s2, sigma 2s2 anti-bonding, and then pi 2px 1 and pi 2py 1. That will make it as 1 plus 1, 2, 2, 2, 4, 6, 8, and 10. So, what will be the bond order of boron? This will be half minus number of bonding electrons minus anti-bonding electrons. What you have got as an answer, Kritika?
Mom, I didn't do it, mom.
Why?
I wasn't able to do it.
Okay. What about you, Shweta? Ananya, have you got the answer? Okay. Ritika, can you explain me from which point you are not able to understand what I am saying? Is the writing configuration clear to you?
Yes, mom.
Is it 3?
Even I have to find it out. How many bonding electrons are there? See, sigma 1s2 is one bonding orbital. Whatever is star marked is an anti-bonding orbital. Sigma 2s2 is another bonding orbital. Pi 2px is another bonding orbital. And pi 2py is another bonding orbital. So what we get? 1 plus 1, 2, 2, 2, 4, and 2, 6. Right? Now talking about the anti-bonding orbitals and the electrons in them, this is 2 plus 2. So this will be 6 minus 4 divided by 2. That is 2 by 2, that will make it as 1, right?
Yes, ma'am.
Now, is there still any issues in this?
No, ma'am.
I'm just again checking out with you. Maybe I'm really, see, I'll appreciate if you can just explain to me, tell me what is the issue. I can find a different way to address it, right? Now talking about whether it will be paramagnetic or paramagnetic or diamagnetic. Shweta, can you help me in finding it's about its magnetic behavior? Is it para or diamagnetic? See, as I told you, para means it has unpaired electrons. Now, as you can see, it has got 2 unpaired electrons. So that means this compound or this molecule is paramagnetic. In this section, from this section of the chemical bonding, we usually get these type of a question. Find the magnetic behavior. How many unpaired electrons are there? So like you have learned the above, you must learn this one also. So this was it about these boron. Now coming to drawing the unpaired electron, as I have shown here, you can draw these electrons if asked, like this also, right? 2 electrons of parallel spin, they need to be there if you are drawing the structure, right? Now let's pick up the next molecule. After B2, we'll be doing C2. I think you should be able to do C2 now. Again, I'll paste the same thing for your help before you people are able to, let's say, remember this configuration. Carbon is atomic number 6 and 6 plus 6 will have 12. You have to tell me the electronic configuration. Then you have to tell me the whether it is paramagnetic or it is diamagnetic. Then you have to tell me if it is, what is its bond order? Quickly solve these 3. Let us solve it together. As usual, we will be writing sigma 1s2, sigma 1s2 anti-bonding. Then we will write sigma 2s2. Then we will write sigma 2s2 anti-bonding, right? So how many electrons we have used? 2 plus 2, 4, 6 and 8, right? Then we can do it pi 2px2 and pi 2py2. Then we will find out the diamagnetic and paramagnetic behavior on the spaces. Clear?
Yes, ma'am.
Okay. Similarly, we have to do it for N2. N2 and O2 are the most important one. I'll appreciate if you can do it at your own. I'm giving you 2 minutes time. Please solve it for N2 and O2. From this part, you get the question classify, or you get a question justify. O2 is paramagnetic. And N2 is diamagnetic. I believe all of you are writing with me. Uh, Ananya, have you written it? Ritika, have you written it?
Ma'am, doing, ma'am.
Okay, I'm waiting for 1 more minute. See, I have written the configuration of N2 having 14 electrons at first place, right? Sigma 1s2, the original thing is copied down there also. Sigma 1s2, Sigma 1s2 anti-bonding, Sigma 2s2, Sigma 2s2 anti-bonding. This is common, right? And it is a smaller molecule, it will form pi first. So we'll have pi sigma, pi 2px2, pi 2py2, and pi, sigma 2pz, right? I believe all of you have got this. If not, then please practice more. If somebody asks me to find the bond order, so what I will do, it has 2 to 4, 6, 8, 10. 10 bonding electrons, and then 2, 4, total of 4 anti-bonding electrons divided by 2, right? So that means this will be 6 divided by 2, that is 3. All of us know the nitrogen has 3 bonds between 2 atoms, right? So that means that bond order of nitrogen is 3. Now, what about the paramagnetic, whether it is paramagnetic or diamagnetic? I'll say this is diamagnetic, right? Because it does not have any unpaired electron. All molecular orbitals, as I have explained you, can have maximum of 2 electrons. So nitrogen has bond order 3 and it is diamagnetic in nature. Now talking about the oxygen, now this molecule is a larger molecule. In this, formation of sigma bond is easier as compared to the pi bond. Therefore, we will follow the second configuration. That is sigma 1s2, sigma 1s2 anti-bonding, then sigma 2s2, sigma 2s2 anti-bonding. Till this point, I'm again repeating myself. This is same in both the categories. In this case, we will fill sigma first. So the moment I fill sigma 2pz2 here, I have 2 orbitals of equal energy, right? Following the Hund's rule, I will put 1 electron here and 1 electron here. Now, at this moment, I know this is a paramagnetic compound, right? Now, talking about its bond order, let's quickly count the number of bonding and anti-bonding electrons. So that will be 2, 4, 6, 7, and 8. 8 minus 4. This one and this one. 8 minus 4 divided by 2, 4 by 2, that will make it as 2. And we know oxygen forms, or O2 molecule is formed by 2 pairs of electron between 2 atoms, right? So that is O2. This is, as I told you, they say O2 is paramagnetic. Go back to the question again. O2 is paramagnetic, but N2 is diamagnetic. The reason being that N2 being a smaller molecule follows the first configuration, and the oxygen being comparatively larger molecule follows the other configuration, in which the sigma bond is formed first and pi bond is formed second. That is why they are, one is diamagnetic and other one is paramagnetic. Now, the word of caution, if you mix these two configuration, if you write oxygen using the first one, that is, you are writing oxygen with this one, what will happen? You will get diamagnetic oxygen and your question will be incorrect, right? So please, again, revise the concepts of hybridization. Very important for you. Atomic orbital and molecular orbital can be compared, and then only your building of the concepts will be thorough. So with this, I'll end the class. And if you want to take the homework, I'll give you one. No, these are the different species having nitrogen. N2, then N2 plus 1, N2 minus 1, and N2 minus 2. You have to write the configuration and find their bond order. Is it clear, Ritika, Shweta, and Ananya?
Yes, ma'am.
Please note down N2,
ma'am.
N2 plus 1, N2 minus 1, N2, 2 minus. Write their electronic configuration and find their bond order. Don't be afraid if you get a bond order in fractions. There will be bond orders in fractions. Means 2.5, 3.5, you will get those. Clear? Any doubt to anyone? And have you noted down
No,
your
ma'am.
homework? Okay, have you noted down your homework? Okay, then let's end the class. Have a good day.
Thank you, ma'am.
Thank you, ma'am.
Welcome.